Welcome. So in this presentation, we are going to explore how CPUs work and why they are one of the most important technologies in modern computing. GPUs as no longer just a graphics hardware; they are central to the artificial intelligence, scientific research, and large-scale data processing. So I will cover. So in this lecture, I will cover what a CPU is, sorry, what a GPU is, how it is evolved, how it differs from CPU, and how its architecture enables parallel processing. So by the end of this lecture, you should have a practical understanding of how GPUs accelerate computation and why modern systems depend on them. So what is a GPU? A GPU or a graphics processing unit is a processor designed to execute many operations simultaneously. That is parallel processing, massive parallel processing. So unlike CPU, which is optimized for complex decision making, a GPU is optimized for repeating the same operation across large data set. So example is a CPU is like a professor solving a problems one at a time with a deep reasoning, whereas a GPU is like a classroom of thousands of students solving the same step in parallel. For example, so imagine adjusting, if you are adjusting the brightness of a 4K image, a CPU could modify pixel sequentially, whereas a GPU can modify millions of pixel at once. So this is why GPU excels at tasks like image rendering, machine learning, matrix multiplication, scientific simulation, etc. So the key idea is throughput maximization, total work completed per second. That is throughput means maximizing the total work completed per second, and the speed of this GPU is very high. It will be around 82 trillion second trillions per second. You can just imagine what is the speed, 82 trillions per second. Next we'll see about evolution of GPU technology. So GPU evolved in response to increasing computational demand. So in the 1990, GPU was were used as fixed function devices. So they performed only predefined graphical tasks. The first introduced GPU is GeForce 3. So later developers could not program them, so they were hardware pipelines. That is a fixed function devices, so they can't able to program them. So they just used as a hardware pipelines. So in early 2000, programmable shaders allowed the customer instruction. So this opened the door to the creativity and advanced visual effects. The version is GeForce 6. Then between 2006 and 2010, unified architecture made GPU cores more flexible. Instead of specialized units, cores became general purpose. GeForce 8, at present we will be using this GeForce 8. Next transition allowed GPU to perform non-graphics computation. So from 2010 onwards, GPU entered into the GP GPU era. That is what will be called as a general purpose GPU computing. General purpose GPU computing from 2010 to at present. So researchers began using GPU to accelerate for many applications like weather modeling, financial simulation, deep learning. So today modern AI systems depends heavily on the GPU acceleration. Next we'll see the difference between a CPU and GPU. A CPU and GPU are built with fundamentally different design goals. CPU mainly has few powerful cores for latency, optimized for latency, that is finishing one task quickly, sequential execution, control focus, and whereas GPU has thousands of small cores optimized for throughput. We'll be having thousands of core, high throughput, parallel, repetitive workloads. So you can see the diagram also. This is CPU will be optimized for a sequential manner. We'll be having a few powerful cores, GPU, CPU core, and here we'll be having many small cores, what we'll be calling as a SM, streaming multiprocessor. So if you are multiplying millions of number or training a neural network, you want repetitions and scale. That's why where we'll be using the GPU. As for CPU, if you are editing a document, running on an operating system or managing memory, you need a decision making and branching where you'll be using that CPU. At present, modern computers combine both CPU and GPU. So we'll discuss what is inside a GPU architecture. As I told, GPU consists of many small core processor called as streaming multiprocessor, the repeating units. So each multiprocessor will be having processing cores, what will be calling it as a CUDA cores, wrap, scheduler, registers, shared memory. So thread execute in a group of 32, what will be calling it as a wrap. Thread is the basic unit. So this design avoids overhead and maximizes the efficiency. So registers store immediate per thread data but extremely low latency. So in general, we'll be having registers first, then shared memory, followed by your global memory, what will be calling as a VRAM. So registers per thread storage, shared memory is fast on-chip memory. So we'll discuss next about the memory hierarchy. Shared memory allows fast communication within a block of threads, and the global memory provides large capacity storage but high latency, that is large off-chip memory accessible by all streaming multiprocessor. For doing the mathematical things and logical operations, I will be having ALU. CUDA cores, specially meant for executing instruction in parallel. So this is a memory hierarchy in GPU architecture. So registers will be the fastest one, or will be having the cache memory. So memory placement is one of the most important performance factors in GPU computing. Registers are the fastest and closest to the computation. Shared memory is slightly slower but allows teamwork between the threads. Global memory is large but slower and must be accessed carefully. So registers, for an example, we say registers are like notes in your hand. Shared memory is a table everyone shares, and global memory is a warehouse across the room. So efficient GPU programs minimizes the long distance memory access. This diagram denotes the graphics pipeline overflow, how we are converting a 3D geometry into pixels through sequential stages one by one. If you are doing rendering, it has to be done in a fraction of second, and these process will be happening altogether in a fraction of second. Mainly this graphics pipeline denotes how you are going to convert a 3D geometry into pixel. So the first one is vertex processing. It transforms a 3D into coordinates, then followed by the primitive assembly, groups vertex into shapes, then we'll be going for rasterization, convert convert shapes into pixel fragments, then fragment shading, we'll be applying colors, lightning, output merging is the produces the final image. So in this diagram also we can see that transforms transform coordinate transform 3D coordinates. The 3D coordinates will be converted into shapes, normally triangle in shape, then convert into pixel fragments. Then we'll be applying the colors and effects. And the last one is output merging. We'll be getting the final image. Millions of fragments can be shaded simultaneously, enabling the real-time rendering in games and simulations. Next part will be CUDA thread organization. So GPU programs uses a hierarchical execution model. Threads, as I told, these are the of execution, smallest units of execution. So threads will be grouped into blocks. Blocks share the memory and synchronize. Blocks grouped into grid. Grids scales across the entire GPU. So I'll be grouping the threads into block. Block will be grouped into threads. If I'm grouping 32 threads together, it forms a wrap. Already we have seen that wrap scheduler. A combination of 32 threads form the wrap. Block group of threads sharing the shared memory. Then grid will be having collection of independent blocks. So one thread per pixel in an image or one thread per element in a matrix. We can say it as, so thread is the basic smallest unit in the CUDA thread organization. So this is the smallest one. What I can say it is thread per pixel in an image. If you are taking an image, one thread denotes each thread denotes a pixel, and or if you are denoting in matrices, so each element denotes a thread. So thread indexing so identifies there are certain numbers or names have been given to identify which block it is, which thread it is, the dimensions, etc. So block ID generally denotes the which block a thread belongs to. across the three format, across the axis x, y, and z dimension. 3D means I will be having three dimension x, y, and z. If I am going for 2D, I will be having x and y only. So each thread nodes its block index and thread index. Using these values, we can compute a global thread ID. Please take a note on this. So global thread ID is equal to block index plus block dimension plus your thread index. So this model scales naturally to billions of threads. We are not having a single thread. We will be having the billions of threads. So in summary, so GPU or processors are designed for large scale parallel execution. Their architecture, memory hierarchy, and thread organization allow them to process massive workloads efficiently. So they power modern AI, graphics, and scientific discovery. So understanding this GPU is an essential for anyone working in high performance computing.